Hello again. Today we're going to talk about Chapter 2, and we're just specifically going to just cover chapters 2.2 to 2.6 for today's topic. Now, before we get started, you're going to need a few things printed out. One being the note sheet that's presented for this section of notes. This one has a larger area for definitions, and on the back, it has the examples that will be presented in this presentation. These examples are performed in the end talk of this notes discussion. The beginning of our notes is going to start with the background history of atomic theory. And so for that, you're going to need this printout of the atomic timeline. And what you're going to do with this is going to be a helpful reference guide for you. The dates for most of these key points in the timeline have been printed above. I have one of the names printed in a spot where you would need to tell me the date, and then you're just going to outline the rest. What are the discoveries that they made that were poignant to the discovery of the atom? And then at the bottom, you're going to draw a rough sketch as to what their view of the atom was at that time. This will be helpful for you for any quizzes and tests that we will have. And lastly, you'll need, of course, our periodic table. This is located in the reference section under modules in Canvas. And so that way you can have that to write on as you see fit. Let's get started. Okay, so we're going to start very far back in time, 400 BCE. And the Greeks, the philosophers, here we have Democritus' statue sketch showing here. The word atom comes from the Greek word atomos, which means indivisible. And so to relate that to atoms, right, we can't divide a carbon atom up anymore. We won't have carbon any longer. We would have small subatomic particles, which on their own do not make up that element. Atoms make up all of ordinary matter. So if chemistry is the study of matter, we need to understand atoms. So Democritus in 460 BCE, his idea with atoms, this was just a thought experiment now. There was no way of doing the proper scientific method at this time. And so it was just a lot of philosophy and just deep thought about the world around them. And so he had wrote, nothing exists except atoms and empty space. Everything else is opinion. So having that idea so early without the scientific background, the scientific data that could back that up, is pretty astounding. He proposed that there were many different kinds of atoms, and they each had their own shape and size. So depending on the substance, the atoms of it would be different sizes and shapes, and that they moved randomly. So I have a couple examples here of his theory that iron atoms, because iron was a very hard material and it was gray, that the iron atoms themselves would be very hard and gray. But he proposed that they were attached together via some hooks, and that would help understand why iron was a material that you could hammer out and make shapes with it. Whereas with clay, clay is more stretchy material, it's more brittle than compared to iron. And so he proposed that the clay atoms would have some kind of ball and socket joint to allow them to kind of pivot. And that would explain different properties that clay had versus iron. And then also look at the color there. The clay is kind of a reddish brown color. This was the color of clay that they would observe in their surroundings. And so the clay atoms then were proposed to be the same color. So let's get a proper definition for the atom. The atom is the smallest identifiable unit of an element. Okay, and we can create atoms. I'll show you on the next slide a periodic table showing how many atoms, how many elements, have we made versus ones that are natural to our world. And so this is a picture of the Large Hadron Collider, which is a particle accelerator. It's located right on the border of France and Switzerland. And to give you some perspective, the red box in the center of that picture, I've just focused your attention on a person standing there. So this is a humongous instrument of technology. And basically what it does is it forces particles in opposite directions of each other, and they go around very, very fast, and then they collide. And the idea is when they collide, they will kind of merge together and form a larger particle than the two that they are separate. And so there's an image on the left side of the screen where you can see that atom A and atom B being different, they're collided together, and some of it, not all of it, sticks. Some of it sticks and is larger than the two original atoms, which is that green color, and that would be a new element with new properties. These are very unstable, though, so they only exist for fractions of a second, but if they are confirmed with the interior of the Hadron Collider, it's made of a bunch of signal-absorbing material that then gets translated to a computer screen, then we would say we've made a new element. It gets a spot on the periodic table. Here's that periodic table picture I was mentioning a moment ago. So in the gray are all the naturally occurring elements on Earth. And so there are 92 of them, basically going all the way up to uranium. Numbers 1 through 92, 92 is uranium. You can dig anywhere in the Earth and find these elements. The green, it says they're extremely rare in the universe, and they're usually synthesized. And so that's astatine and francium up in the body of the periodic table that you see there. And then we have a row of others down here in the bottom block. So francium and astatine are very, very, very chemically reactive elements. They're very big as well. So they're unstable being so big, holding their particles together. And so they naturally decay, and when they do that, they lose some of their particles and become smaller elements. So that's called radioactivity decay. And so they naturally do that. And so there's only fractions of each of these elements existing at any point in time because they decay so quickly. And then it says here, in addition, scientists have succeeded in making 26 synthetic elements, and those would be the ones you see in pink. Now I know your eye is probably going to that pink one in the very middle of the periodic table, technetium, and you're probably wondering, well, why is that man-made? It's in the middle of all these other natural elements. Well, the reason is that technetium, it's not stable on its own, so it's not found in nature. It's, again, another one of those kind of, the combination of the subatomic particles is such that the ratio of them together is unstable. It's too big for it to hold together. And so it just naturally decomposes and breaks apart into smaller elements. So it was kind of a hole in the periodic table for quite some time until we were able to learn how to synthetically make elements, and then we were able to make it that way. Okay, so looking at your atomic theory timeline handout that I showed in the beginning, we're going to focus on key events in the discovery of atomic theory. So we're going to start here in 1789. Now look at the equipment in this picture here. It's a lot of glassware, some bending to some tubes there. They're using open flames. He has an inkwell there to write his notes. So very early looking chemical equipment, not very fancy or advanced here. So Antoine Lavoisier, he formulated the law of conservation of mass. This states that in a chemical reaction, matter cannot be created or destroyed. So when a chemical reaction occurs, the total mass of the substances that are that are reactants, will be able to total up together as new products. You're not going to gain mass or lose mass. You're not going to create matter or destroy matter. And so here's an image from the textbook that helps you visualize this. So sodium by itself, elemental sodium, is actually very soft metal. It has similar consistency to silly putty, and you can actually stretch it. It's pretty neat. but it's very, very reactive. And so if we were to take a sample of sodium and then chlorine gas, which by itself is a yellowish green, very toxic gas, we combine these two together, they have a chemical reaction and we get ordinary table salt out of that. And you can see how the sodium is represented by these purple elements. It's a block that's representative of a solid structure, right? Very organized. And then our gas is just the opposite. It's very disorganized. There's no structure to it. They're just the particles of chlorine bouncing off the insides of the container at varying speeds. And then when they're together, you can see the green and the purple are integrated into this one solid structure. So this says up at the top, the mass of the reactants equals the mass of the product. So if we were to add up the masses of these two elements, noting that chlorine has a 2 there, meaning it is diatomic, meaning 2 atoms. And there are several of elements that exist like this in nature. They're too reactive to be by themselves, and so they naturally kind of bond with each other. So we have 2 atoms of chlorine, so we'd have to multiply this mass of chlorine by 2, and then adding it with the sodium, we get 19.6 grams. Okay, so if we add up 1 sodium and 1 chlorine over here, we're going to get 19.6 grams sodium chloride. And so the mass did not change. Okay. Our next scientist that we have is Joseph Proust, 1797. He was a French chemist, and he is um, credited with coming up with the law of definite proportions. So he said that all samples of a given compound, so now we're talking about not just atoms, but compounds, which are atoms chemically connected to each other, like a molecule. But a compound is a term used with the word element to describe their identity. An atom and a compound, an atom and a molecule, atom and molecule are more quantity terms. So, like what you have in front of you, but the identity is element versus compound. He's talking about a compound, regardless of where you get them or how they were made, they're going to have the same proportions of those elements that make them up. And so let's take a look at that in a little more detail. So another way this is phrased is the law of constant composition or definite proportions. So it could be called either or. I call it definite proportions. So that's what you'll hear me use in class and going forward. So here's an image that may help you decipher his law. So we have 1 gram of carbon dioxide, and this is how carbon dioxide is bonded together. It's a linear structure. We have an oxygen on either end of it, carbon in the middle, and these lines represent connections or bonds. So we would say that this is double bonded here because there's 2 lines. So the oxygen and carbon is double bonded on both ends. Okay, so we have 1 gram of this molecule. We can figure out by mass, we'll see that in a little bit actually, the percentage of one element to another. And so in a molecule of carbon dioxide, it makes sense having 2 oxygens that it's a higher than 50% ratio of oxygen that's present. And then the rest is making up from carbon. Now, if I have 16 grams of carbon dioxide, I do the math, work out the ratio, I get the same values for how many oxygens per carbon there are. So it doesn't matter how much of the material you have, the ratio is constant. 1 carbon, 2 oxygen is going to come out to these percentages here. So now we look at a different chemical. This is carbon monoxide. This is the dangerous one that you may have heard of. Okay, carbon monoxide is deadly, and it's triple bonded. See that there? 3 lines. Okay, so 1 gram of this, if we calculate the ratio here, here we have a closer split because there's only 1 of each element. We have 57% oxygen to carbon's about 43. Okay, so that's what Proust meant by his law of definite proportions. Next, we have an English chemist. He's actually a literature teacher that did chemistry more on the side as a hobby. It was very um, prosperous if you had the ability to afford the famous glassware. It was very expensive to make, much more precise instrumentation at this time starting to come out, and it was kind of the cool thing to do to show that you were wealthy if you were able to have this kind of labware. And so John Dalton, he's an English teacher, but he kind of dabbled in chemistry in his garage, let's say. So he liked the scientific discovery process. Here we see the scientific method now finally being followed. And he was looking at Democritus's idea. Now, this is now much, much later, right? Democritus was BCE time, and now here we're just a few hundred years ago in 1803. But Dalton has a very important um, portion of this atomic theory story. And so in 1803, he proposed his theory. His idea of what the atom looked like was similar to Democritus in that it was just a solid sphere. So his is sometimes called the billiard ball model, which is why I put the picture of billiard balls right here to help you if you're not, a huge pool fan. That's to just conjure that up for you. So with Dalton's theory, he just thought of it as a full sphere. He didn't talk about connections like Democritus did. Uh, he didn't talk about different substances, how they would be different. He just figured they were all solid spheres. Okay, so that's the key takeaway for Dalton. He also outlined his theory into four main points, and you need to know these. So let's go through each one. So he proposed that each element was made up of tiny, indestructible particles that he called atoms. Okay, so each element is made of these. He also said all atoms of the same element will have the same mass and other properties that distinguish them from atoms of other elements. He just didn't know what at the time. Okay, he would say that through his research, he believes atoms would combine in simple whole number ratios to form compounds. Okay, that goes back to point number one, right? If they're indestructible, then you're always going to have at least one. And so you're never going to have half of one. So looking at my model kit with water here, I can't break these little spheres up and have half of one or a third of one. So they're always going to combine as a whole piece. And so that's what he means by point three. Lastly, in point four, he says atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way they're connected to other atoms. And that was a lot to say at this time. Okay, so a bit similar sounding to Proust theory, we have Dalton coming up with his law of multiple proportions, okay, not definite, multiple. And so that is elements combining in different ways to form compounds, but the mass ratios are the whole numbers. So this is just another way, multiple proportions, meaning multiple different combinations, but they're still acting as whole units, these atoms. And you could pause the video and take a closer look at this image. Okay, so I have to mention this gentleman here. So this is Dmitry Mendeleev, and you may have heard of him in high school chemistry. He is credited with coming up with developing the very first periodic table, the first gentleman who wanted to figure out a way to organize the elements to study them better and to learn from them better. So you can see a very rough sketch off to the side of his notes on the different elements. One thing that you can also notice here is that as you look at the symbols, you see some for sodium, carbon, let's see what else is there. Hydrogen's listed, oxygen, um, nitrogen, I see. It's a much, much smaller list than our current periodic table. There were not nearly the number of elements known at the time. Now we're in 1869. That still is not that long ago, considering we're in 2023. So then we go to 1897. We have J.J. Thomson. He worked with cathode ray tubes, which, if you recall the older TV screens, which is one is pictured here, the back end of the TV taken off, this is what it looks like in the uh, inside that protective plastic, is this cathode ray tube. It's right here. And so these old TVs are sometimes called CRT, cathode ray tube television, because it contains this device. Now, they didn't have televisions in 1897, so this was more the early stages of using this technology. And so, with his cathode ray tube, Thomson discovered the electron. He found that the beam of particles that went from one end to the other, they traveled from a negative electrode to a positive electrode. And let's take a look at that. And so here's an image of this device, very plain cartoon image of it. So the normal operation of a cathode ray tube, we've got this particle of electrons, this energy, right? Just think of electricity. And we pass it through this charged beam, and it hits onto the end here on some kind of screen so you can see it. So Thomson, what he did is he placed magnets on either end of the cathode ray tube, and he saw that the beam here would bend, so it's not hitting the same spot as it did without the magnets. And he saw that it would bend and be attracted to the positive metal plate, the positive part of the magnet. So if that's positive, the beam must then be negative because of how magnets work. And so he proposed that he had found the electron and that they were negatively charged. And so Thomson's model became known as the plum pudding model. And this is a typical English dessert. He was English, and so it makes sense that he would relate it to something that he's familiar with. And so it looks like, kind of like a raisin bread pudding type dessert. And the idea behind it is like the cartoon that you see on the right. It's it's a mass of positively charged matter, and the negative electrons are kind of suspended within it. So they're stuck inside. They're not moving. They're just stuck inside this big positive mass. So more familiar to us, it's been referred to as like a chocolate chip cookie or a blueberry muffin. If you can picture these different things, you can picture Thomson's model. And so his is typically called the plum pudding model. Now, J.J. Thomson's son grew up to study physics and chemistry as well. And so what he did is kind of interesting. He's looking at his father's data, and his father's data with the cathode ray experiments showed that electrons behaved like a particle. But his son did an electron experiment. You can see it's still a cathode ray tube here, and he put some gold foil in the middle and saw that it would split when it hit the gold foil. So there was a diffraction pattern, and you can see that on the right. And so his son's experiment showed that electrons behaved like waves, like sound waves, kind of echoing out. So they're kind of contradictory with this electron. What is it? Well, even now, we're still at kind of a tough point. We can't say with certainty one way or the other if an electron is a particle or a wave. So we just say it's both because we've had these two experiments to confirm that. We haven't been able to get any more specific data to say one or the other, or if it really is both. And so this theory is called the wave-particle duality. All right, Millikan's oil drop experiment. I don't believe this was on the timeline handout. It's kind of unfortunate, but this experiment usually gets pushed away when you compare it to the other scientists. What he's credited with doing is finding the charge. So not only is it positive or negative, which we found earlier with Thomson that it's negative, but what's the value of it? What's the magnitude of that negative? Okay, and so that's what Millikan's credited with doing. However, it's not on your timeline sheet. Okay, um, this is an idea of his schematic here, where he had basically like a perfume spray here for some oil, and it would go through this this plate that was positively charged, and then he hit it with some ionizing radiation. So that could be just any radioactive source, and he funneled it into this container that way. He's looking through this viewpoint here, and again, a light source because radioactivity and radiation is not visible without some kind of light to it. And so he saw that the charged oil droplets stayed suspended in what looked like an electric field to him. And so that's how he proposed, in doing calculations from there, that the electrons each had a charge, you see it there on the screen, negative 1.96 times 10 to the negative 19. So it's a very, very super small value, but these electrons are very, very small. But that's what he's credited with finding, the actual value of the charge for the electron. So that brings us a little closer to current times. We have 1909 here. Ernest Rutherford, New Zealand fella, worked under Thomson, that's Thomson Sr., and he agreed with his model of the atom, that plum pudding model. He wanted to replicate that and prove it further that it was the valid knowledge of the atom. But he had something unexpected occur with his experiment. So let's take a look. He took positively charged alpha particles. And so alpha particles are just a specific type of radiation. Radiation can occur as alpha, beta, or gamma particles. Alpha are basically helium nuclei that are being given off by a radioactive element. And so he's aiming this at a thin sheet of gold foil. Here's an image of what his experiment looked like. And so that ring that you see around the gold foil is a special filtering material that would glow as it got struck by the particles going through this gold foil. And so the idea was he was going to show the source, which is contained in lead. Lead will isolate the radiation so it's not going out in all areas. He had a little pinhole in the front so it would focus the radiation out, aimed it at that gold foil, and what he saw was they didn't all pass straight through. That's what he expected. They would all just go in a straight line and go right through. But what he saw was some would deflect. About one in every 20,000 or so would be deflected. So it wasn't a lot, but it was enough to be kind of concerning. Well, why is it doing this? Every once in a while, there'd be one way off. You could see them kind of banking off almost horizontally from where they're being struck. And the detector's measuring these with that light. So what he found was, we have here the plum pudding model, what he expected the alpha particles to do, go straight through, but his actual result was what you see here on the right. And so what he had concluded from that is that there must be a centralized, dense region of some particles that once in a great while, his alpha particle hit it and deflected off. And he proposed that it was small because it was so infrequent that we had a particle deflect. Most of them did go straight through. And so that showed the first knowledge of a nucleus in the center of an atom, that small centralized part of the atom with some kind of solid concentrated particles, later to be found protons and neutrons. So that changed his mentor's model. So here's what Rutherford's theory is basically about, three parts. So most of the atom's mass and all of its positive charge are contained in that small centralized nucleus. He also proposed that since most of the particles went straight through the foil, that most of the volume of the atom must be empty space. But there are tiny negatively charged electrons located there. And lastly, he found that there are as many negatively charged electrons outside that nucleus as there are positively charged particles within. So the atom itself has no charge. Electrons, protons, different charges, same number of them though. so they're canceling each other out. Okay, so then that brings us to the final subatomic particle that needs to be discovered here, the neutron. And so Rutherford's model was very widely accepted, but scientists realized that we still have to find this other particle that's accounting for the mass. And so one of Rutherford's students, this gentleman, James Chadwick, demonstrated that the previously unaccounted for mass was this neutron. And so you see a schematic of his experiment. Okay, we have alpha particles being emitted again. We're told that they used polonium, which is a radioactive element. It's PO on the periodic table towards the bottom. You want to find that. He sent it through a small sheet of beryllium, which is Be on the periodic table. You can find that near the top. And so then he had some particles that were detected. They were non-ionizing, but they were able to penetrate through the beryllium. So it was solid enough, but it just didn't have a charge to it. Then he had some wax, paraffin wax, which is a very tight network. Waxes are very complicated, large structures. So it was like a big screen where some particles were caught and some were able to pass through. And so he saw that these neutrons, that he would then call them, were caught in that paraffin wax, but the protons were able to pass through and they were picked up on a detector at the other end of this instrument. So I have this picture that is pretty cool to just kind of summarize these last three fellas here. So Chadwick discovered the neutron, and he was a student of Rutherford who discovered the proton. And Rutherford was a student of Thomson who discovered the electron. So it's neat in itself to have a student discover something that's in the same realm as their teacher, their mentor, but to have this kind of lineage is just really cool. And then adding on to that, Thomson's son coming in with his electron experiment too. It's just kind of neat. So before we go on with now just some math to calculate the different particles here, that's all of the atomic theory portion of the chapter. All you would be responsible for is again what you end up filling out on this table that's included with the notes. So where you found these notes, you'll find this document, this atomic structure timeline. And so just the scientists that are featured on this paper are what you would need to know. You would need to know the dates, okay? And it may be difficult. I wasn't very good with history to remember the specific number dates, but you should at least know who came first, second, third, and so on. You should then know what they're credited with finding, maybe a description of their experiment, like Rutherford's called gold foil, Thomson was the cathode ray tube. You can write up in here, and then a picture. You saw pictures throughout this presentation of what their model was as it was experimented on and found more and more detail throughout the years. So that's what you would need to know as far as atomic theorists and scientists. The last part of this chapter that we're covering today is going to focus on just atomic structure and how do we know how many particles each different element has. And so that's where we're going to right now. This is where you'll want to have the note sheet out. That was also where you found these video notes, and we'll be highlighting the examples that are on the back. You'll also be given a lot of definitions here to place in this box. So let's get started. So we're told that the mass of a neutron is similar to a proton. So we basically say that they're equal. One proton would weigh the same as one neutron. Together, they're located in that nucleus, which is the mass of the atom. So protons and neutrons added together would give me the total mass of that atom. And so this talks about a helium atom is 4 times massive as the hydrogen because it has 2 protons and 2 neutrons. So here's a picture of each element. A hydrogen atom is the simplest element. It's number 1 on the periodic table. because it has one proton. There it is in the middle. It does not have any neutrons in the nucleus. So its mass is 1, and this is atomic mass unit, AMU. It's not grams, because we're talking about a single atom here. And so we have another unit to describe that such small quantity, and that's called an atomic mass unit. So hydrogen has a mass of 1 with its 1 proton. Helium, element number 2, is 4 times as large because it has 2 protons, the 2 plus signs here, but also 2 neutrons, which just have mass. They do not have a charge. But the mass of the atom is everything in the nucleus, protons plus neutrons. There are 4 particles here, so the mass of helium becomes 4 AMU. Okay, so you've probably seen images like the one that's on the screen there before. These are the basic components of an atom. So you need to know what they are. The electron is negative and it's found outside the nucleus. It circles in orbits. Neutrons are located in the center of the atom in a location called the nucleus. This is much different from the nucleus in a cell that you may have learned about in biology class. This is much, much smaller, and it doesn't have any kind of encapsulation border like a cell nucleus does. So this is just an area in the center of the atom. It's just condensed there. So the nucleus of an atom has neutrons, which have no charge, they're just mass, and protons in the same space, which are positively charged and have the same mass value as a neutron. So they are essentially equal in mass. This chart just goes through each of the 3 subatomic particles in a comparison here. So their actual mass in kilograms. Remember, that's our base unit of mass in metric. So you could see how the neutron and the proton are virtually the same mass. Okay. The electron's much, much smaller. We have it still raised times 10 to the negative 27, but look how that front number would have to be presented to keep it in that same scale. It has to be 0.00091. So the electron is still much, much smaller than the proton and the neutron. So much so that we don't count electrons in the mass of the atom. They're just so small that they don't contribute much to the overall mass, so we exclude it from that calculation. But if we look at the mass in this atomic mass unit, we could see it's a 1-to-1 ratio of proton to neutron. And again, the electron is not counted. What about the charge? And it says relative because we're comparing one subatomic particle to another. So relative to each other, the proton has a positive 1 value each. The neutron is no charge, so it is 0. And the electron has a negative 1 charge each. And so then we can put a value to that charge, but you don't need to know that. Okay, elements are defined by their number of protons. So looking at the periodic table, the number of protons is going to be that number that's above the element symbol, which the symbol are the letters. Okay, so the number that's written above it, that's the atomic number, and that tells you how many protons there are in an atom of that element. The number of protons is the identity of the element. There are no elements that have the same number of protons but are different elements. It's a unique number. So we can look at these 2 examples. We have a balloon where if we took the helium out of the balloon and took a look at it, way zoomed in, the helium nucleus has 2 protons, these red circles. And the carbon that's on the end of your pencil tip has 6 protons. So they are different elements because they have different numbers of protons. So here again is another image of the periodic table like the one that I've asked you to print out for this lesson. So similar to that, it has the number above the symbol. That's the atomic number. That's the number of protons. So for any element on the table, I could ask you how many protons there are, and you can tell me by just looking at that top number. Then we have the chemical symbol. The symbol is the one, two, or sometimes three-letter designation of that element. Then lastly, we have the whole name of the element written out. Okay, there's usually another number for each box. You'll see it on your periodic table that you had printed out for this, and you'll always see that those are decimal numbers. That's the mass. Okay, just caution, some periodic tables that you may find if you're using Google to search for other periodic tables, there's a style difference where some periodic tables will switch the atomic and the mass number. So you just want to be careful. That's why I have you using all the same table that I've provided so that you won't have that confusion amongst each other. But I just want to warn you that sometimes periodic tables are presented with that atomic and mass number switched. The mass number is always the decimal to kind of help you. All right, so each element has its own unique atomic number and unique symbol. Chemical symbols, either one, two, or sometimes three, like I've mentioned, abbreviation. So the chemical for helium is He. For carbon, it's just C. For nitrogen, it's just N. And then if we go to the periodic table here, let's see. Oh, this one is completely updated. So what I was looking at are these elements down here, 112 to 118. So these were a few years ago given proper names, but before that, they were just given a placeholder name, which was their number, their atomic number, so like 112, but it was written in Latin. And so 112 in Latin is unundunium. So it would have UUD as its symbol for breaking down that word. But now that's been replaced with proper names. All right, example one. This is a sample question. Which element contains 50 protons in its nucleus? Take a second, look at your table, and think of which of these choices is the right one. All right, let's see how you did. The answer was tin. So tin, you see here on its little block from the periodic table, it's got that 50 number up at the top. That's the atomic number. That's how many protons it has. Now let's talk about differences in neutrons. So we can have the same element with different numbers of neutrons in their nucleus. It's still the same element because the number of protons is not going to change. Neutrons don't have a charge, so they're not going to change the chemical activity of that element. They're just mass, so they're just going to change the mass of the atom. So here we have an example of neon. Neon exists in three isotopes, or three atoms of the same element, where just the neutrons are different numbers. So isotopes are when you have the same element, but different masses. And so if we look at this, we'll compare each of these in a second. So now, here's another confusing part. This is a notation called isotope notation, the way that these symbols are written. Okay, the format for isotope notation is to write the mass number on top and the atomic number on the bottom. I didn't make it up, I just teach it. But that's isotope notation, because if we look at it, we're comparing the top numbers here. We have 20, 21, and 22. That has to be the mass number because we're saying they're all the same element, neon. And if we look at the number on the bottom here, they're all 10. And that's the atomic number for neon. So it is switched in this case with isotopes. So you need to know that. If you're given the information that we're talking about an isotope, you need to know that the mass is on top and the atomic number is on the bottom in that case. So in reading this, for this first one, we would have 10 protons because that's our atomic number. The mass is the total of protons plus neutrons. So if the top number, the mass number is the total, and I know a portion of that total with the atomic number being the protons, subtracting these two numbers would give me the number of neutrons. And that's what we're going to do. So we have 10 protons defined by the atomic number. The total mass is 20. So 20 minus 10 would give me 10 that must be neutrons. The electrons are 10 because the protons are 10. And remember that different charges are going to be the same number of them to cancel out. In this next example of neon, we have 10 protons again. Here they are. The 10 electrons in this cloud here around the nucleus. They're there still. But now we have 21 for a total mass. So we subtract 21 minus 10, and we get 11. So for this middle isotope of neon has a greater mass, and it's because it has one more neutron than the previous atom of neon. Next, let's look at the third isotope. So this one has a mass of 22, and it still has the atomic number of 10. To find the number of neutrons, we're going to subtract 22 minus 10, and we get 12. So this is neon because it has 10 protons, but it's a heavier neon because it has 12 neutrons. Atoms that have the same number of protons but a different number of neutrons are called isotopes. All right. So how do we know how much of each isotope, like what's the more common one? We can relate the amounts to each other, and we come up with a percentage. That's called the natural abundance. And we'll be using this in a calculation later on in a different video. So the isotope, we're told we have titanium here, and we have an isotope with a mass of 46. We have one with a mass of 47, 48, 49, and 50. Here they're not showing the atomic number because we're told they're all titanium. So find titanium on your periodic table. Its symbol is Ti. Okay, that's Tl. Be careful, right? We want an I. Titanium. It's right here. Its atomic number is 22. Okay, the one over here that it's usually mixed up with is number 81, thallium. That's a L. This is an I, so that's titanium. So with titanium, we can find the percent abundance, or it can be told to us. And so what that says is how much of each isotope, how common is it? And so this one here, 73% common, right? Abundant, tells us that the isotope with a mass of 48 is the most abundant type out of the 5 different isotopes that it could be. So here's just a generic symbol, general symbol of what you see on the periodic table. Okay, the mass number is written on top for isotopes, the atomic number is on the bottom, and then X is representing the chemical symbol. You take a look at your table, there are no elements with the letter X. That's just a general placeholder to show you the spot where it is. The mass number, again, there's no element A, so that's just a letter just to hold that spot to show you where the mass number is written. And then the same with the atomic number. There is no element Z, and so that's just, again, a placeholder to show you the spot where the atomic number is written. And this is another way we can write isotope notation. This way shows just the mass number. Again, because we're talking about the same element, it's understood that the atomic number would be the same. Neon with a mass of 20 can be written either with the symbol Ne, dash 20, or you can write out the name neon dash 20. There is another difference here that's important to mention. The symbols, the first letter of each element symbol is capitalized, always. But when we write out the whole name, it's lowercase. It's not a proper noun. So it's not like your name. The element names are not proper nouns, so they are not capitalized. So here we can look at our chart again. The symbol for neon with a mass of 20 has two different versions. Neon 21 could be written this way or the other way, and then lastly, neon 22. This is a typical format for how these questions are asked, a table. Some of these would be missing, and you would be asked to fill them in. And so we have the number of protons. We could find that from its atomic number. It's the same element, so they have to be the same. The number of neutrons are what makes them all different from each other. That's the difference between an isotope and a typical atom. So these numbers have to be different. The mass number has to be different because the protons and neutrons added together give me that. And then the percent abundance, again, will be calculated in a different video. But from here we can see that the most abundant type of neon that we would encounter, 90% abundant, is this neon with a mass of 20. All right, example number 2. Argon. Argon is in a group of the periodic table called the noble gases. We're going to cover the periodic table in the next video, but the noble gases, like argon, are not reactive unless you pass an electrical current through it. So on the bottom of this picture, you see a pretty nice purple neon light, right? You would call it neon light. It looks like storefronts that have the neon designs in the windows. But this is the gas argon. And when argon has an electrical current placed through it, it reflects purplish color from the electromagnetic spectrum. And so that's the characteristic color of argon. So back to the question. An argon isotope has a mass number of 40. How many neutrons does it contain? All right, let's see what you figured out. If you said 22, you are correct. And the way we find that is we look at argon on the periodic table, and we see that its mass is written as 39.948. Now, when we're doing these calculations, we need to round the mass numbers. The mass number is calculated, the one that's on the periodic table, the mass number there, is calculated by that percent of isotope abundance. So it's not a true number. It's a summation, a weighted summation of all the isotope versions that there are for that element. And each element has a different number of isotopes available. So with that said, we have to round that to a whole number because I can't have a fraction of a neutron. So this has to come out to a whole number. So 39.9, we're going to round that to 40 and use that as the mass. And we were told that in the question we were using 40 as well. We subtract the atomic number because we know that the mass is protons plus neutrons, and the atomic number is just the proton. So taking the difference will give us how many neutrons there are, and subtracting 18 from 40 gives us 22. Here's example 3. Carbon has two naturally occurring isotopes, carbon-12, which is the more abundant at almost 99%, and then carbon-13, which is around 1%. If the circles, which we see here are red, represent protons, and squares represent neutrons, which image best represents the carbon-13 isotope? So for this one, you're going to need to count and see which one of these is correct. Okay, let's go over the ones here and see if you're right. The first thing I'm going to look at with a question like this It says that I have carbon here. Carbon on the periodic table is right here, and its atomic number is 6. So that means it's defined by that atomic number. The number of protons must be 6, or else it's not carbon. So the first thing I would do with the question like this is narrow down to the pictures that just have 6 protons. They said the circles were representing protons. So if we look in A, I have 1, 2, 3, 4, 5, 6 circles. That's a carbon atom. So that one passes for the next round. Okay, let's look at this one. We have 1, 2, 3, 4, 5, 6, 7. B is not carbon. With 7 protons here, this is a nitrogen atom. So it would not be an answer just because of that. Now looking at C, 1, 2, 3, 4, 5, 6. C is also a carbon atom. So the choices here can either be A or C. Now for this question, it's asking which one of these choices represents C13. 13 is the mass. If we subtract 6, which is our proton number, from 13, we'll get 7. And so I need 1, 2, 3, 4, 5, 6, 7. I have that here. My choice was A. How'd you do? All right. The last topic for this chapter in this video today is ions. So with isotopes, we talked about the neutron number being different for the same element. Ions are going to be where we change the electrons and have the same element. Ions are the reason why chemical reactions occur. The ions, which are relating to the electrons, they're the furthest edge of an atom in that electron cloud where they exist. So they're going to be the first to interact with the electron cloud of an adjacent atom. And it's these ions that determine whether those two atoms that just touched are going to react or not. More on that story a little later, but that's the importance of this topic. So ions just mean they have a different number of electrons than protons. The typical atom, right, a neutral atom, the ones right off the periodic table here, it's understood that the atomic number is protons and electrons. These are all neutral, no charge. If we change the number of electrons, we're going to have an ion. If we take electrons away, electrons have a negative charge. If we remove them, we're going to have more protons than those electrons in that case. Because we'll have more protons, our overall ion that we just made would be positive. So any positive charged ion, we see here sodium with a plus, that's understood to be 1 if there's no number there. We call those cations. Negatively charged ions, such as fluorine here, again, that's understood to be a 1 next to the negative if there is no number written there. Negative ones are called anions. So you need to know the difference between those terms. If we're getting a negative ion, we have more negative particles. We have more electrons. So anions are formed by gaining electrons. Cations are formed by losing electrons. Here's example 4. How many electrons would be present in an oxygen -2 anion? So the way to answer this question is to look at oxygen right off the periodic table. When we find oxygen on the periodic table, we see that its atomic number is 8. Oxygen has 8 protons and 8 electrons. If I'm forming a -2 anion, that means I'm gaining electrons to be negative. So I need to add to my electron count. 8 plus 2 more would give me 10. So I have 10 electrons. The electrons themselves are negative things, but here we're counting how many of those negative particles we have. This is a very confusing topic for entry students, so give yourself some patience when you're doing this and just keep talking yourself through, as I've just showed you here, on how to determine the total. So that's it for this video. Go ahead and try the homework that's up there now, and if you have any questions, you can always ask when I see you again. Thanks a lot.